Welcome to Brain Vision.
The pendulum in a grandfather clock is made of brass and it keeps perfect time at 17 degrees Celsius. How much time is gained or lost in a year if the clock is kept at 28 degrees Celsius? Assume that the frequency dependent on length for a simple pendulum applies. So this time dependency on length is given by tau for time, because not to confuse it with T for temperature, is equal to 2 pi root L over G, where G is a gravitational constant, L is the length of the pendulum, and L is the length of a pendulum. So we aren't given the length in the question, so we need to make length the subject of this equation. So we have length is equal to G over 4 pi squared, tau plus delta tau, is 4, ignore that, is G over 4 pi tau squared. And so if we perturb this equation here and make give length a delta L, a small increase in the length, because of the small temperature increase, then we expect to see a small increase in the period that it takes. So length plus delta L is equal to G over 4 pi squared tau plus del tau squared. So this just represents the length of a pendulum for a given time period, with a small increase in this case. And we are going to call this equation 1 and this equation 2. And equation 3 will be our formula for linear thermal expansion, because we have a pendulum, a thin pendulum, a wire, basically a brass wire that's expanding as a function of time. So we get that delta L is equal to alpha L delta T, where delta T is change in temperature and not to be confused with tau. And we're going to call this one equation 3, and we're going to substitute in equation 3 into equation 2 here. So doing that substitution, we get that L bracket 1 plus alpha delta T is equal to G over 4 pi squared tau plus del tau all squared. And we're going to call this one equation 4. And we're going to start a new page because this one's getting quite full. So we're going to go from, our next step is to substitute equation 1 into equation 4. And we're going to do that one over leaf to give ourselves a bit more space. So doing that, we get that G, and selecting G over 4 pi squared tau squared. So substituting just to double check, so G over 4 pi squared tau squared, and then the rest of that, so 1 plus alpha delta T, 1 plus alpha delta T is equal to, just double checking this off, is equal to G over 4 pi squared tau plus delta tau squared. So G over 4 pi squared tau plus delta tau squared. Perfect. Oh no, the square needs to go outside. Right, so squared. And we observe that we can divide both sides by G over 4 pi squared to eliminate that term. And we're also going to do a Taylor expansion here. We're just going to expand the brackets here. And we're going to observe that our change of time in our pendulum compared to a year is going to be very small. So a term that's delta tau squared will be 0. or will be close enough to 0 to justify removing it. Now, we could actually solve this all the way through with delta tau squared in the equation and get a quadratic at the end, but because it's so negligibly small compared to the time period, it will give the same answer, and it saves a fair amount of time doing this. So we're going to write this out. So tau squared plus alpha tau squared delta t is equal to tau squared plus 2 tau delta tau. And the delta tau squared, as I said, is just negligibly small. And we're going to subtract tau squared from both sides and then divide through by 2 tau on this side, which gives us delta tau is equal to alpha tau delta t over 2, which is our formula. So what we have here, we can look this up. So alpha for brass, the coefficient of linear thermal expansion for brass is alpha equals 19 times 10. That should be a 9. 19 times 10 to the minus 6. We're going to say our time period is 1 minute. So this is going to give us our rate of time change per minute. So the units will be minutes per minute, but it would also work for years per years. But we need to convert from years per, because our answer is in minutes per year. So we would need to convert from years per year to minutes per year, or from minutes per minute to minutes per year. It's easier to multiply through because time periods don't work in base 10; they work in base 60 and 24, which makes it easier to multiply through rather than divide. So that's simply why we're going to work from minutes per minute to minutes per year. So tau is equal to 1, and the change in temperature is given by 11, equals 11. And we're plugging this into a calculator. We get that delta tau is equal to 0.00209, and this is mins per min. I mean, in principle, it would be unitless, but it just makes it easier to see. It's basically just a ratio. So to convert that to minutes per year, we need to multiply by 60, then by 24. So the answer that we need, we have to multiply by 60 to get minutes per hour, then by 24 to get to minutes per day, and then by 365.25 to get to minutes per year. So doing all of that gives us delta tau is equal to 109.9 mins per year, which is our final answer.